Hello everyone. So today we are going to talk about the third law of motion. In the last class we have seen that first and second law of motion tells us about inertia and force. Now what is inertia? Inertia was a kind of property for which any kind of objects want to retain its previous state. And what was force? Force was nothing but the transfer rate of momentum so that we can change the state of any object. Now, today we are going to talk about Newton's third law, which is every action has equal and opposite reaction. Now, like how to say this, like how to realize the fact. We know that in the last scenario we have seen that every object wants to stay in its previous state. So obviously when you are transferring momentum, that means you are trying to change the state of this object, automatically the object will give you some hindrance. That means the object, as the object wants to be in that state, so this object will give you one kind of hindrance, and this hindrance will be equal and opposite in in terms of the direction what you have applied. So if you have applied a force F, so this object will give you some reaction force R in such that R will be if R is a vector, so this will be opposite of your F vector. Now this like if we what you say take a equivalent, if we think that these forces are equivalent, okay, in that case only. Okay, so now the question will come, if every object is giving reaction force, then when we want to push something, like if we have one kind of block and we are giving some force F, and if this block is giving back some kind of reaction force R, so that means R and F, they both will cancel each other and the total force will become zero. That means this object should not move. But in our real life we see that when we push something, that object moves. Now the question, then why this F and this R is not cancelling each other? To understand this scenario, we have to take help of two situations. So in the first situation we have a block where F1 force is applying in this direction, as well as your F1 force is applying in opposite direction. So if I am applying equal forces on this block A in two different directions, so what will happen, the total force will become zero, because F1 and then we have again minus F1. So if we talk about the value itself, so you can see that the direction between these two, so I can write F1 square plus F1 square plus 2 F1 F2, not F2, this is F1 again, so F1 square, I'm writing like this so that you can understand. And then we have cos 180 degree, because the angle between F1 and this F1 is actually 180 degrees. So obviously from here you will get that this is 2F1 square minus 2F1 square, so it's nothing but 0. So that means my total force is 0 in this case. But when we take some situation like where I have only one force acting on a block, this A block, and I'm giving F1 force, and that's why this A block is giving another reaction force which is opposite of F1, so the value will be F1 only. So in this case the situation should become 0, but it will not become 0. Why? Because you see here ki in this case F1 is acted on A block. So I am giving F1 force upon A block, and A block is giving F1 force on me. So the question is that the two forces are acting on two different points. In case here F1 force is also acting on A, and this F1 is also acting on A. So that means my resultant force, all of the forces are acting on a single object. But in the second case, so this is first case, so in the second case what is happening, the force which I am applying, that force is acted on the block A, whereas the reaction force which A is giving is acted on me. So action points of forces here is different, whereas the action point is same here, and that is this block. So in this case action point is different. That's why we cannot add or subtract these two forces, because they are acting on different points. Cannot cannot add or subtract them. Okay, so this is the thing that why everything moves and these two forces does not cancel each other. These two forces don't cancel each other. Okay, now what is the significance of this reaction force? So see one thing, when we stand on any floor, we know that our earth is always pulling us downward, right? So the gravitation force is acting downward and earth is pulling us. So that means when earth is going to pull us, we are stuck by the ground. If ground was not there, so we should go inside earth, but because of this surface or the ground, this ground is giving hindrance so that we don't go beyond it, right? So we don't go in the inside the earth. So that means as this surface is giving hindrance, so that means we are giving this force of gravity upon this surface. So that means the surface is experiencing a force which is nothing but the gravitational pull with what gravity is pulling us. So as this surface is getting impacted by the gravitational pull, so it will also keep some reaction force. So this reaction force will become upward, right? So this reaction force will be in upward, and that is called normal reaction. So this normal reaction is actually responsible for what we feel weight. So we feel heavy due to this. So why we feel heavy only due to normal reaction? Because see, if you have a biscuit and you are giving the biscuit to someone else, so the taste of that biscuit can be felt by that person to whom you are giving the biscuit, but you cannot feel the taste because you are giving to him. If he gives you something, then only you can experience, right? So in the same manner, like we are giving force which is nothing but the gravitational pull to the ground, so that force we cannot feel. But because of Newton's third law, it is not that Newton has made it, it was there in our universe forever, but Newton discovered it. The property Newton has recognized. So the normal reaction is given by the ground to us. So because ground is giving normal reaction force to us, so we can feel this force, and that's why we feel happy. Okay, so like if you see that if you have a weighting machine, so if you have a machine where you can take weight, so if you see that if you put something like 500 gram object, so in the ground, when the machine will be in ground, it will show you 500 gram. But when the machine is falling, like if you set the machine in such a way so that it will fall, okay, so it will be under free fall. Okay, so there is nothing, and then you have your 500 gram, what you say, so this is 500 gram object, so 500 gram here also you have given, but in this case it is falling, it is not sitting on the ground, so it is falling. So when it is falling, so you can see one thing, that the what you say, weighting scale will show 0. Now the question is there, why it is showing 500 gram in case A when it is in the ground, and why it is showing 0 when it is under free fall? So this is because of the normal reaction force. So so you can see here, in the case when it is on the ground, it is giving this 500 gram is being given by the weight to the spring, and to the spring balance machine, and to this balance machine to the ground. So ground is having a force, that's why ground will also give some normal reaction force, due to which this machine can show you the data. But here when it is under free fall, so that means the gravity is working it downward, the gravity is pulling it downward, but the problem is that no one is there to give the reaction force. As a result, the what you say, the indication is showing here that it is 0. So you can feel the same thing when you are jumping. So when we jump from some place, we feel weightless, right? So now the question is coming, that when we feel weightless when we jump, as well as one place is there when we feel weightless, and that is the lift. So in the lift we feel weightless, even heavy, when lift is going down or up. So let us talk about this situation. Let's say you are standing on the lift. So the weight that you can feel is nothing but the normal reaction. So let's say this is the normal reaction which is given by the lift, and let's say this is the force that you are giving to the floor of the lift. So this is your mg, because we know that earth is having like a gravitational acceleration g, so we know that force equal to mass into acceleration. So instead of acceleration we can write here g. So the weight of any object can be written as m into g. Now we know that earth is pulling us downward, that's why we will give mg force to the ground of the lift, as well as the ground of the lift will give us reaction force n. So in normal case, when there is no up or down, our normal reaction is equal to mg, so we will feel our normal weight as well. But when the situation will be changed, when the lift is trying to go downward, Now you see that when the lift try to go downward, what will happen? See, your body has some inertia. So even if the lift is going downward with a acceleration, your body will be what you say, will be showing the laziness, that is the inertia, and it will try to be in the previous state. So that means your body wants to go in the upside, so that even if the lift is going down, the body can stay in its previous state. So if your lift is going with a acceleration downward, your body will have some inertial force. So this force, okay, for like this is a kind of hindrance, you can say. Well, okay, so this force will be your ma. Though the lift is going downward, but your body will show a property for which it will try to be in its previous state. So your body will produce or will show some inertial force, one kind of hindrance, which will be upward. Okay, so I'm writing here, this is inertial force which happened due to inertia. Due to this inertial force, your body will be showing the laziness, and it will try to go in upside direction. So now if we calculate all the force and balance it, so we can see that in the up direction normal is working, and in your ma, that is your inertial force, is working, and in the downward direction your gravitational force is working. So you can see that the normal reaction, that means your feeling, will become mg minus ma. So that means it is g minus a. That means you can see that in normal cases, like when the movement was not there, it was n equal to mg, that is the feeling was my actual weight. But in this scenario we have normal reaction equal to mg minus a. That means the feeling will be lesser, so I will feel that my weight has decreased when the lift is going down. Okay, and let us talk about when the lift is going up scenario. So in the similar way, we have this lift here, and this is you or me, and then you are giving some kind of force, okay, to the floor, and floor will be giving you back normal reaction force in up direction. Okay, so this is your normal reaction, this is your mg, and now the lift is going upward with a acceleration. So the lift is going upward, but your body, because of inertia, to keep its own previous state, it will be go in the downward direction. So the inertial force will work now in the downward direction in order to restore the previous state. So the inertial force will be in this case ma, which is acting downward direction. Okay, so your body will experience a willingness to go in downward direction because of inertial force. So now we can see that normal is working upside, and the downside ma and mg both are working. So you can see the feeling, that is the normal reaction is increased now. That means you will feel more heavier when the lift is going upward direction. The same situation will happen when you have a thread and a stone is tied in the last corner of the thread, and you hold another portion of the thread with your finger. Okay, so if you push the thread upside, what will happen? Okay, let's talk about the general one first. So in the general case, what will happen? This ball wants to go downside because of gravitational pull, but someone is giving hindrance to the ball. So that's why there will be a force tension which is balancing so that the ball don't fall. So T is the tension, or you can say this is kind of reaction force simply. Okay, now in normal situation T is balancing mg, and that's why the ball is not moving, it's just staying there. Now what will happen if you suddenly pull the whole system upward with a acceleration? You can see that the ball, because of the inertia of the ball want to be in its own state, that means the own place. Now if you pull the thing upside, so the ball because of the inertia the ball will be going in the downward direction. So that means the ball will give inertial force in downward direction. So this force is why this force, so that it can restore its own state. Okay, so now if we do the balancing, so we can see tension is equal to ma plus mg. That means the tension of the string will increase, and you can see that if your a is too high, that means if you give a jerk suddenly, what will happen? The tension will be so high that the string or the thread will not be able to tolerate it, and the thread will be torn. Okay, so this you can do in your home and you can see easily. Now if we talk about another situation when you have the same thing and now you are moving your finger downward direction suddenly, so what will happen here? If you give a sudden downward jerk, now you can see that tension was working as usual and mg was there as usual. Now when you are trying to go in the downward direction your hand, then what will happen? This stone want to restore its own state, so it will be going in the upward direction to restore its own state. So the inertial force now will be upside, that is your ma. So now you can see that T and ma both are working and mg is there only alone in the downward direction, and all of these forces are working on a single point, that is the stone. So T we can write here mg minus ma, that means the tension has decreased. And you can see that if you just move your hand suddenly downward, you can see the tension will be so less that the string will be almost like this. Okay, so you can do this easily and you can see this in your home. When you're trying to go in the downward direction, the string become loose, and when you pull it upward with strong jerk, it can be so tense that it can turn off even. So today's today's topic was this one, that is the reaction force and the third law of Newton. Now because of this third law, now one thing I have told you earlier about circular motion. Now if you remember, then I have told that in case of circular motion there are two types of acceleration. Now if the speed is not increasing, that means for uniform circular motion, so in this case also you have seen one kind of acceleration is always there, though in case of uniform circular motion omega is always constant, that means omega is not changing. What was omega? That the rate of rotation, you can say, one kind of, so that is even constant, but still one kind of acceleration was working in the inward direction, always towards the center of that circle, right? And we told this acceleration to be centripetal acceleration. centripetal acceleration. Because of this centripetal acceleration, one kind of force is there that is called centripetal force, because we know acceleration always provides some force. Okay, is always like corresponds to a force. So that means if some object is rotating in this circular path, then always centripetal force is acting on this particle so that it can rotate always in a circular path. It does not go in tangential direction. So so that it can be bended in all of the points on the circle, this force, centripetal force, is working. So that means the centripetal force someone is giving on the object so that it can it can be confined to this circular path only. So that's why there is another reaction force which is felt only by this object who is rotating, and that is called centrifugal force. So centrifugal force is nothing but the reaction force of the centripetal force. Okay, so who can feel this centrifugal and who can feel centripetal force? Now centripetal force means someone who is outside of this system, he can feel centripetal force. Why? Because someone who is outside of the system will see that the point is rotating in a circular path because it is having always a force towards the center, so that every point on the circular path, the direction of the particle can be changed. Okay, so the direction of the particle is changing in such a way so that it is confined in a circular path. But centrifugal force, who can feel the centrifugal force? Who is rotating only himself. So the particle can feel this. Even you can feel this thing when you travel in a bus and suddenly in a turn like this, your bus take a turn and you feel that your body is going outward, so you stuck in the window suddenly, right? So this force for which you stuck in the window is the centrifugal force. Okay, now you will see then, like in case of this stone, it is not going in outward. See, it is not going outward because something is there to hold it, and that is centripetal force. But in case of you, the bus is rotating, but you are not stuck by anything. So because of your inertia, your body wants to go in outward direction, because force, the centrifugal force, is acting on you and nobody is there to stop you, like to hold you, right? So that's why you feel this outward force. So today's topic was basically regarding this two force, like this reaction force. One more thing is there, that is centripetal force and centrifugal force, both are same in terms of value. So centrifugal force is also mv square by r. Okay, so today's study will be this much only, and in our next class we will talk about some mathematics, some numericals regarding this. So bye for today, and I will meet you in my next